Good morning, good afternoon, good evening, wherever you happen to be. I'm Juancho. This is Computer Graphics. We're going to talk about more triangles today. I want my rectangles. See, we're going to do rectangles today, so I can put my rectangle shirt on today. I've pushed the second assignment up there. It will be available for this class. It'll be on another GitHub classroom. What did we do last week? We talked about pixels. We talked about images, and most of you have finished the first assignment, which is just manipulating pixels, getting used to the idea that there's pixels. We talked a little bit about TypeScript, and you should have seen a pirate duck and a pirate cat as a part of this assignment. What we're going to do today in this pre-lecture and in the class, we're going to understand how to render a single triangle using hardware acceleration. So last week we did a triangle in software and GPU. Today we'll talk about why that's not the best way to do computer graphics, and we're going to introduce you to the idea of a graphics processing unit, and you'll see how we set data up from that. So hardware accelerated graphics is started off as a separate card, and you would send data to that card. Now on my computer in here, it's all built into the CPU, but there's different parts of the silicon that are focusing on general purpose computing, which is what the CPU does, and graphic processing, which is what the GPU does. So last week we did this triangle. We went through the tedious find the line, the two lines, and you saw that we wrote an algorithm for a triangle that, given any triangle, you can just do it, right? And as an exercise in class today, we're going to extend that, and we'll do a little bit more of our software rasterizer, and then we're also going to talk about how we set things up for the GPU. But basically, what we did in class last week, the hardware is going to do for us. We just have to know how to set stuff up for that. Why is this important? Well, you saw that when we did the rasterization of that triangle, we were doing a lot of math. For every edge of the triangle, for every scan line, we had to do some math to calculate where they intersected, and then we filled out the pixels in between that. Imagine doing that for models of 80,000 triangles, 100,000 triangles. You can see that there's quite a bit of math involved there. When you look at the layout of the capabilities of a CPU versus a GPU, CPUs are handling a whole bunch of data. They're fetching data from the internet. They're fetching data from the hard drive. They're communicating within themselves. So they can do some math. They have these arithmetic logic units. They also have a lot of control. They're controlling the hard drives. They're controlling the network card, all of that stuff. But the GPU isn't talking to the internet. It's not talking to the hard drive. It's simply taking a bunch of triangles and doing processing for them. So what they have done in the industry is they have added a whole bunch of silicon to the GPUs, and it gets more with every iteration, such that we can do more and more processing. And then you'll see, you've also heard a lot about how it's being used for Bitcoin mining. Well, that's mathematics. AI, there's a lot of kind of mathematics stuff that you need to do there as well. So it's kind of interesting architecture. The way to think of this is, it goes back to that diagram of the little person who could draw triangles really fast. That's what your GPU is. It's a coprocessor. So we can hand off jobs to the GPU because it is separate, and we say, hey, go do all of these things, and then the CPU can go read data from the hard drive. It can go see if there's any data coming down over the network card, all of that stuff. So we basically package our data up and we send it over to the GPU. We say, do your stuff. In a typical game engine, we send data to the GPU either 30 times a second, or if you're really going for the high end, you do 30 times a second, 60 hertz. And then while you're waiting for the GPU to do its work, you do some other work, like you might do your physics interpolation. You might look at, see what packets came from the other players, calculate intersections with bullets and people, and all that kind of stuff. And then the GPU finishes its work, renders the image, and then you package up a bunch of data based on how you've changed the world, and you send it back to the GPU again. And there's a process that the GPU goes through. You'll see in the upper right-hand corner this little bunch of squares with arrows. We'll dig into them. Don't worry if you can't see them right here. And at the end of the day, the GPU finishes rendering the triangle, which is what we're going to do today, or we did last week. And then it says, hey, I'm ready for the next job. Very simple job. So how do we program a GPU? There's the hardware is very specific. There's the OpenGL hardware. There's also Direct 3D API. All of these vendors like AMD, NVIDIA, and Apple with their silicon on their chip, they provide support for these APIs. OpenGL, we're going to use WebGL2, which is essentially OpenGL. DirectX 3D, Metal, and Vulkan are different ways of accessing the hardware. They all have their advantages. As we discover inefficiencies with OpenGL, Apple introduced Metal as a better way of dealing with the hardware. The hardware didn't change underneath, just the API, and Vulkan is also a new one. We are going to be working with a modern WebGL. It's not the most modern OpenGL. You can see that there's OpenGL is up to 4.5. We're working in OpenGL 3, and I will highlight a little bit of the differences. But if you know how to use OpenGL 3, you are ready for dealing with OpenGL 4 and OpenGL 4.5 because the philosophy of how you access the GPU and how you program it hasn't changed. We've just made it more programmable in different places. So it used to be that the early GPUs basically said, we're going to do everything for you in such a way. So on the CPU, we would generate a bunch of vertices, we would process them, and we would say these are the primitives, then we would hand them off to the GPU. It would generate the primitives for each triangle, it would process them, it would generate the fragments. Fragments are those tiny little pixels. Remember when we said set pixel in the lecture in the class last week? That's what a fragment processing is. It was very simple for us. And then at the end of the day, you write pixels to the screen. And we'll talk more about that later when we get to that. But then it turns out that we wanted to be able to do some vertex processing. So in this particular thing here, the vertex processing, which was the transforming the vertex by multiplying it by a bunch of 3x3 matrices or 4x4 matrices, as we'll see. But that's just math, right? That's the stuff that the GPU is actually very good at. So we moved it into the CPU, the GPU, and we made it so that you could actually customize that yourself. That idea is that we would have a shader or a little mini program that would you can say, okay, for this particular model, I want it to be displayed in this way, and for this model, I want it to be displayed in this way or transformed in this way, and then the lighting and the model and how it looks is what we do as a fragment processing. So we're going to actually allow you to write code for that. And in this particular lecture, we have to do both of these things because that's kind of the basis of modern OpenGL. And then we added some more capability, more cores. Those little gray squares that you see in there are kind of the things that can act independently. So each one of those can render a triangle really quickly or a multitude of triangles. They're going up with every iteration of the GPU that we see. You have more of these cores. And now we see another yellow box that showed up, which means that there's another place that we can write programs. So the first one, you'll see we have the OpenGL 1, OpenGL 2, and OpenGL 3. OpenGL 3 has a vertex shader, a geometry shader, and a fragment shader. That's where we're going to be, but we're not going to be dealing with the geometry shader. This is, you'll hear people talk about the fixed pipeline. The fixed pipeline means you couldn't write, you couldn't customize what was happening on the GPU, and now we have to actually, there is no default behavior, so we actually have to write minimal shaders. We actually have to upload programs to the GPU. But more GPUs means more interesting. You can follow up and do some research on what some of these other shaders are doing. They're pretty cool. When you're looking up references on the web, you'll see WebGL and you'll see WebGL2. Do not use any of the WebGL examples because they use the fixed pipeline. We are looking at WebGL2, so we don't want that. So how do we work with the GPU? Well, there's basically the ability, we need to actually figure out how to send data to the CPU, the GPU, and then we need to tell it what to do with that data. So this diagram here, we're going to focus on vertex shaders. All of this stuff we're going to ignore for this course, and then this one here we're going to focus as well. And then all of the yellow things that we see here, those are going to be things that we're not worried about. Here's another view of this pipeline. We take our vertices and our primitives, we process them into transformed vertices. The rasterizer is the hardware. We don't control that, and it gives us a bunch of little pixels, and it says give me the colors for that, so we write a program for that, and then we take the output of that and we merge it into the frame buffer, and then that goes into the frame buffer. And you saw that a little bit in the exercise that we did last week, where we set a value in the frame buffer that was just a number, and then that was displayed on the web page, and that's kind of similar to what happens. The GPU itself doesn't actually put color on the screen. There's a final process that reads values, a 2D array of color values, and then displays it on the screen. So the big idea, there's two ideas, and I said before, how do we take our data and package it up such that we can send it to the GPU? And the other one is, once we've sent that data to the GPU, how do we tell the GPU what to do with that data, right? And so the first one is we need to package our data into buffers, and we'll introduce the idea of what a buffer is. A buffer is just a big array of data, nothing magic about that. And the second idea is to write programs. We'll introduce to you the programming language for shaders, which is GLSL, GL shading language. We'll see that. So the shaders are the programs for the GPU, and we're going to write these programs. Let me say that. So basically the idea here is that I like Mike's starring here. You can see that you have your app here with TypeScript or C or C++. It doesn't matter. It's all the same thing. And it packages data into a buffer, and then it says, hey, off you go, and then we send a program to the GPU, and the GPU goes off and does the thing. We're going to, in the class today, we're going to do two things. One is we're going to take the triangle render that we did last week, and we're going to extend it very quickly, so we can kind of have an idea of what the hardware is doing in there, and then we're going to switch over and work on assignment 2 and get you on your way to doing that. We'll definitely get the first part done, and hopefully you can get work on that, and then you can focus on some of your other courses if we get this assignment done. And then, so let's see. This is what we're going to try and do in class today. We're going to try to display this triangle in WebGL. So let's define the variables for the positions for that. So last week I told you that the origin for computer graphics for frame buffers is in the upper left-hand corner. Today I'm telling you that the origin is in the lower left-hand corner, because the computer screens were generated by electrical engineers, and they counted where the scans started from. And computer graphics was defined by mathematicians, and they think of the origin as being in the lower left corner, kind of what you did when you do graphs and stuff like that. So, and there's a simple way of switching between the two of them. So, um, I can't shield you from that. Sometimes you're dealing with the origin up at the upper left-hand corner, and sometimes you're dealing with the origin in the lower left-hand corner. That's just the way it is in computer graphics. There's just two standards that live together. So in this particular diagram, this is 0, 0 is right in the middle. So this is minus 0, minus 0.8, minus 0.8. This is 0.8, minus 0.8. And this is 0, 0.8. And so you can see that data here. We've displayed that there. And the way that we're representing these is as an array. It's an array with 9 elements, and we're actually going to store the value here, the x value, the y value, the z value, and that will just continue over like that. And there we go. So what do we do with this? We've defined this guy. Now we need to tell our hardware to draw this, and there is quite a laborious process. We're going to have to do quite a bit of detailed work to get there. So just bear with me, and we'll go through this in the class as well. And it's actually important that you understand what we're doing, but it really does go back to this idea that we have data that we want to send to the GPU, and then we have shaders that do stuff with that data. Okay, so that's what we're going to do. So we have our data. Here's our data, and we want to go and do that. So we put that into a vertex buffer object. It's an OpenGL feature that provides methods for uploading vertex data: position, normal, color, etc., etc. We transfer that data over to the GPU, and then we say, okay, go ahead and use it. So first thing we're going to do is show you how to do that. Okay, so I define an array of type float32 array. In TypeScript, that means that we're using floating values that have 32 bits per value. Now, it's knowing the size of your data is really important, because when we transfer the data over to the GPU, there's no type information that's associated. There's just a raw array of bytes, and we have to tell the GPU what that data is, how big it is, and how to process it. And that's what we're going to go through here and deal with that. So a vertex buffer object allows us to put data in there, and it can be the color of a vertex, the position of a vertex, a texture coordinate, the normal of the vertex. All of these things we can just package in there, and then our GPU can use that, because we're going to write programs that are tied to the data that we send. So we talk about object-oriented programming. You'll hear me talk about objects. For OpenGL, it's based on a procedural language called C, and an object is just a buffer. It's just an array of things. So don't get confused. Don't think that there's an object-oriented programming paradigm in here. TypeScript is object-oriented. We use that to generate data objects, and those data objects are then passed over to WebGL, OpenGL. Yeah, we'll talk about that. So essentially, the way that OpenGL thinks about things is it has these blobs of data, and it has a particular ID. So it's just think of it as a map between the handle integer and some sort of data, and we let the GPU handle that stuff in the background, and we essentially use these numbers here to tell the GPU this is the data for this and this is the data for that. So let's go have a look at this thing with WebGL. So the first thing we do is we create a position buffer. As you're reading the examples on the web, you'll see that in C and C++, the functions look like GL bind. In TypeScript, the way that they implemented it, we use GL dot. But essentially, these function names here are exactly the same between OpenGL and WebGL. So we're going to try and display this triangle. So we will define a buffer, and we say, hey, Mr. GPU, create a buffer. And then we're going to say this buffer is going to be of this type. So this returns an integer, essentially. It returns a WebGL buffer ID. And then here we say we're going to use this for an array buffer. That means it's a vertex buffer, a color buffer, a texture coordinate buffer. This is kind of like floating point numbers, and you'll see that. But so now what we've told, and again, to repeat, we've told the GPU, we've asked OpenGL to create a buffer. At this point, that buffer is just the place where information is going to be put. So when you go back to this drawing here, we have asked OpenGL to create a buffer, and it's given us a handle, something like that. And we don't need to know what it is. We just need to pass that back in again. So we're good. So here we say, give us a handle to a buffer, and here we're going to say this buffer is going to be used for vertices or texture coordinates or something. In this particular example, it's going to be for the vertices, the X, Y, and Z position for the vertex. Then we take the triangle vertices, and we'll see this in class, but this is an array of data. It's basically one of these guys. It's a float 32 array. We'll see that in class. So what we're doing here is we're saying, okay, we're going to take an array buffer, and here's the data, and then we're going to use it for a static draw. Don't worry about it. It just means that we're using it to draw a triangle. When you read C++, you'll notice that in many of these buffer operations, we also pass in the size of the buffer. JavaScript arrays actually know what size they are. C++ arrays don't. So you basically have to go here, and you have to give the GPU some more information, which we don't have to do in TypeScript. That is the difference. But that's just if you're doing it in C++. So when we looked at this triangle, we drew it like this, but that's not really how the data is implemented in memory. So we put it this way so that conveniently we could think of this here as our first vertex, this as our second vertex, and this is our third vertex. But basically, this is what the computer sees. It just sees 9 numbers. Now, is that is this like X, Y, X, Y, X, Y, or is it X, Y, Z, X, Y, Z, X, Y, Z, right? Because we can send vertices to the hardware as 2D vertices, or we can send them as 3D vertices, or even 4D vertices. So we need to be able to tell the GPU what to do with this data. We're going to so the last thing that we're going to do is we're going to set up the attribute pointer. We're going to tell OpenGL how to process this data. Okay. So in this particular slide here, I have a shader, and don't worry about it. We're going to come back to that later. And you'll see that there's a variable in there called in position, right? That means that's the variable we want data to go into. And we'll come back to that. Don't worry about it. But what's important in this particular case is that I need to couple this position with this. So what I want to do is I want to be able to link these two together, because when we write our shader program, we're going to be taking the position and we're going to be doing something with it. So we need to tell OpenGL how to link these together. So what we do is we're going to ask the program. We have a shader program, and I will show you how to build that in a second. There's two things you have to do. Either you do one first or the other, and they're linked together. So in this case, we're doing the data first, and then we're going to do the shaders, right? So now that I've got this position location, I enable an attribute array. So basically, I'm going to make enable this position location, then I'm going to bind the buffer to that position buffer. So basically I'm taking that array, I'm going to say this position is tied to an array buffer, and then I'm going to say here's how you process the data. And then the way that we tell GL how to process the data is that we have this data is for the position location, and this is how many items there is per vertex. This is the type of data, so it knows what size. Because remember, the GPU just has an array of bytes. So they need to, the GPU processors need to know, am I dealing with 32 bits of data? Am I dealing with 64 bits of data? Or am I dealing with 8 bits of data, right? So you have to we have to tell them, say, okay, when you take data out of this bundle, you take it out 4 bytes at a time or 3 bytes at a time, etc. And when we get to colors, you'll see that there's even more interesting ways of packaging data. Like you can have 8 bits for red, and so all of these things are highly configurable. But the GPU deals in raw memory, and that's part of why we did that exercise of dealing with images and dealing with raw memory again. So now that we've told the GPU what type of data it is, we have this parameter. It's going to be false for most of what we do, but one of the options that you have is you can take your vertex data and you can compress it down into 8 bits or 16 bits as integers, in which case you would say it's normalized, and if it's normalized, it then expands that into a floating point value that either goes from -1 to 1 or 0 to 1. But we don't need to worry about that. And then these final two are the stride, which is how do you step over the data, and for the second part of this assignment, that stride will be a different number. 0 says it's default. So if I say I've got 3 floats and I put a 0 there, the processor will go, okay, I have 3 floats, I'm just going to move 3 floats over and get the next piece of data there. So 0 means default there. And offset is if you are looking for data in this buffer, do you start from the beginning of the buffer, or do you have to move over to the right a little bit because there is other data in this buffer? And in the second part of this assignment, we will be blending position data and color data, and you'll see how that works. Okay. So essentially, the idea is that you have this array. You have a stride. You could say 3 or 0. The default is here because it's packed. And then the offset says start looking for data here. If the offset was 1, then we would start looking here. And then we're all done. We say draw the arrays, and the type of data that is in this array is triangles, and there's 3 vertices that you need to set off. 0 is the first of 3 values, and 3 is how many triples to draw. So we're ready, right? We can just draw our triangle. Yeah, not right. We now know how to send the data to the GPU, and we know how to say to the GPU, go ahead and draw, and the GPU is going to go, yeah, but I don't know what to do because you haven't given me any programs to transfer to do the vertex. I don't know what to do with this data. I really don't. I need to do something with it, and then I need to pass it to the fragment generator, and then it's going to spit out a whole bunch of fragments, and then we don't know what to do with those fragments. So we need to do two things. We need to do the vertex shader. We need to do this person here, and then we also need to do this one here. All of this stuff is happening automatically. So at the point where we say GL draw arrays, we're ready to go, but we don't have this thing in place, and we don't have this thing in place. So shaders are just programs that work in the that run on the GPU. They basically run on each one of those cores, so they run in parallel. We need to compile them, and we need to link them, just like we do with Java or C++. You'll see that. So, how do we go about doing this? Pixel shaders first. There are a large number of other shaders we're not going to deal with at this course, and you expect to see more of these shaders come out as the hardware gets more and more complicated. So here is our shader. This is what we're going to do in class today. So let's break this one apart. A vertex is input. It's moved around. So basically what we do is we're going to take that original position and we're going to run it through the program. In this particular example, we're going to do absolutely nothing with this data. We're simply going to pass it out. We specify the version of GLSL that we're using. So in this class, we're using 300 because we use 3.0. That tells the compiler what features, that's kind of the version of the language, and it tells the compiler you can use this function or you can't use this function. But don't worry about it. We're just using 300. If you want to see what some of the other features are of what are the other extensions of GLSL, you can go look that up on the web. In Java, when we write a function, we have an input. We say function, and then you have parameters, and that's the data that's coming in. In GLSL, remember, these are programs that are running in a very specific place in a pipeline, and a vertex shader is expecting a position. So we can specify a vector in, which is in. So this is a keyword that specifies that there is data coming into this program. It is of type vector3, and we're going to call it position. The main program in a shader is called main. It always is. It returns nothing, but it has side effects. And the side effect that this particular function has is that it's going to write to this special variable or function. So a vertex shader is expected to put data in the GL position variable. And once you do that, then the rest of the pipeline will take over. So we've got this part here. We wrote this little shader here that goes, I'm going to take a vector in, which will come from the data that we sent it, and I'm just basically going to push it out as a 40 vector. And you'll see later in class why this goes out as a 40 vector. It's to do with 3D transformations and stuff. It's kind of neat why we have 40 vectors. So now, once we do that, then the tessellation, the geometry, all of this stuff happens. The triangle gets tessellated, it gets shaded, we do post-processing, we do primitive assembly, and then we rasterize it, which is what we did in the last class. And then now we say, okay, for each one of these pixels, we have a fragment that's coming out. What are you going to do on that fragment? Fragments, again, they're the pixels. We generated a whole bunch of fragments last class, and we were able to kind of go and we just set the color. In this class, I will give you a 3D, a triangle rasterizer that does colors, and then we're going to do some of some other exercise. So it'll make sense to you. A fragment shader is something that runs for each one of those pixels. And we specify a fragment shader using the same language. If you were using a different version of GLSL, you would use it. So for example, if you wanted to use 3.3, which we don't have access to, but if you are playing around in C++ and you have access to some of the more advanced OpenGL, you can do that there. But for our class, it's 300. Out, remember we had that in variable. For the fragment shader, you can specify what the out thing is. So we're going to specify that we're putting out a color of 4, red, green, blue, and alpha. Alpha is the transparency. And in this particular example here, we're just going to render a red, kind of pinkish, kind of orangish triangle. Again, all shaders start with a function called main that has side effects. So this particular side effect is that I have this color, which I've defined as an out vector, that is going to be rendered into that. A lot of these commands that you'll see, you can go look them up. There's Web2 fundamentals. There's also docs.gl. In particular, this one is nice because it'll show you what GL compile shader is available for ES3, which is what we're using. ES2, GL2, it's all to that. So you can go to, if you see an example with some sort of function, you can go and see for which versions of OpenGL or WebGL is this available. So in the next assignment, and what we're going to be starting to work on in this particular lesson, is there's again canvasgl.tsx. This is where you'll be working, and we're going to go through and painfully go through and put the steps for the first triangle. The second one, I've put them there. Go through and with me. You'll go through with me, and we'll kind of add these things step by step. The second one, we can we'll jumpstart you and get you over into the image buffers and index buffers. So we want to render a blue triangle. I've set you up with a framework that has a button that you can change the parameters, so you'll be able to do that. And you'll do that by changing the vertex specification of the triangle. Then, okay, so we've got that. Now we need to compile the shaders. So we've written the shaders. Now we have to compile them. It's quite a bit of work, eh? It's all of this for just one little triangle. So we've got these two shaders, and what we need to do is we need to compile them and build them into a program, because we've got them as text. We understand what they do, but we haven't given them to the GPU yet. So that's what we're going to do now. So here is a very kind of step-by-step. Basically, it's very straightforward, but it's very tedious. What we're going to do is we're going to compile our shader. We're going to basically state, here is the source for our shader, and then we're going to compile it. So we specify, we basically upload the code to the compiler, then we compile it, and then here we see if there's any errors. And we're going to do the same again. We do that for the vertex shader, and then we do that for the fragment shader, and then now, what do you do if you get an error? Well, you have to fix it. It won't work if you have an error. So sometimes I put console error there. Sometimes I throw an error. But basically, you want to make sure that you check the compile error, because if you don't have that, you have a problem. And if you do end up with a syntax error or something like that, ChatGPT and Copilot, ChatGPT is quite quite good at telling you what's wrong with the shader. So you paste the source code for your shader into ChatGPT and ask it what's wrong, and it's pretty good at telling you what's wrong. And so then down here, I create the program. So a program is a container that's going to contain all of the shaders, and then I attach one shader. I attach my vertex shader. Then I attach my fragment shader. Then I link it all together. Again, we could have mistyped a variable, the out and the in variable, and they could be mismatched. So you want to make sure that you check the outcome. So you want to compile the shaders, check for an error there, and then you want to link them together, and then you want to check to see if that's okay. And then at that point, the only thing that you have to worry about is that the logic of your shaders may not be good, but you'll see that from looking at the image. And then finally, we pass this program over to WebGL or OpenGL if you're doing this in a different thing. If you're doing a production environment, it's good use to detach the shaders and throw them away. For the little baby programs that we're doing, that's not necessary here, but it's probably a good idea to get into the practice of. So this is the way it works for OpenGL 3 and up. As they've added other shaders, it's exactly the same thing. If you had a geometry shader or a fragment shader or a tessellation shader, if you add these two, it's essentially the same thing. You create a program, you compile your shaders, and then you add them all to the program, you link it, and then you use it. And then once you do that, then the GPU goes, okay, I now know what to do with data when it comes in, and let's go and let's do it. Okay, so that gets us to the point where we can now draw that triangle. So cool, lots of data being sent over to the GPU. We have little programs that do stuff for us, and we can render it. Now let's have a look at this index buffers. We have this triangle, and there's only one way you can represent this triangle. It's 3 points. Now, the coordinate system is like this, as I reminded you before. But one of the things that we need to do is it's not so important for 2D triangles, but it's something that you need to be aware of, is that because we need the normal of a triangle, i.e. a line that's perpendicular or orthogonal to the face of the triangle, we need to know whether some triangle is facing outwards of a model or facing inwards of a model. And we've adopted the convention in the computer graphics community that if you're looking at a triangle and you look at the order of the vertices, if it's counterclockwise, then that is called that you're looking at the face, and if it's clockwise, you're looking at the back. And what do we mean by that? Well, if I have this array here, and I, that's 0, 1. This is -1, -1, and this is 1, -1. So you see that we've gone in a counterclockwise direction around this array. It doesn't matter which order you do it in, as long as you go counterclockwise in each order. Now, okay, so now we want to draw 2 triangles. We want to make a rectangle. That's why I wore my rectangle shirt today. But the hardware doesn't do rectangles. We talked about that before. So what we can do is we can draw two triangles. So let's define 2 triangles that make up that particular image, that rectangle, right? So basically we have this triangle here. I think I have this. So basically we have this here. Let's go back here, and we can go through and okay. So I want to draw this rectangle. I can draw a line either from 0, 0 to, I can split this into a triangle in two easy ways. I can either do a line that goes from 0, 0 to 1, 1, or I can have a line that goes from 0, 1 to 1, 0. So now, let's just pick that first one. And then look at what triangles we need to draw now. So the first one that we would draw would be 0, 0, 1, 0, 1, 1, okay? And that would draw that bottom right hand. And let's just specify the vertices for the top one now. I'm going to start again at the origin, then I go up to 1, 1, then I'm going to go to 0, 1. So that defines my two triangles, right? And then I can say, okay, draw this as two triangles. Take the first 3 points and make a triangle, and that will result in this triangle being drawn. And then I can say, now take the next 3 lines and draw them as another triangle. And so I get this triangle here. So again, and so that gives me a rectangle. It's 2 triangles. I can now start decomposing all of my geometry into little triangles. In the class, we're going to see what a triangle fan is, and we'll see a triangle strip, some of the kind of early primitives, and then we're going to talk about how to draw arrays, and we'll see that in most cases we don't want to actually do that. But the basic idea here is you can draw everything as a set of triangles. Now, in this particular thing here, we had 6 vertices to display a square. So ideally, how do we do it with just 4? Okay. This one's repeated, and this one's repeated. So what we would ideally like to do is think of this as 3 floats or a vertex. There's my X, there's my Y, there's my Z. There's my first, there's my second, there's my third. So basically what I'm saying is I have 6 vertices, and I can think of these as indexes. I can index into this array because I have 18 floating point numbers, but I can partition it into 6 sets of vertices. Like this. So basically I can draw 0, 1, 2, and then I can draw this one instead. It's 3, 4. This is the other order from what I did in my little example, but there you have an idea. So what we really would like to do is draw this little triangle, but we don't want to send 6 pieces of data over. What we would like to send is 4 vertices, and then tell the hardware how to use those 4 vertices to generate the 2 triangles. So what we're going to do is we're going to create another buffer. We have a buffer for vertex position. We're going to do an element buffer object. It's an element array buffer. And what we're going to do, and this you'll see this in part 2, is we're going to create a new buffer. So we ask OpenGL to create a new buffer here, and then we bind that buffer to an element array buffer, right? Not an array buffer. So this thing is telling us we're going to use this to index into things, and then I'm going to again, part 2, you'll see this. This is the indices of how to use the triangles. There's 3 indexes per item, and then the hardware says, oh, okay, I have a compressed piece of data, but I have this way of looking into it such that I am going to generate my triangles in exactly the same way I did, but I don't have duplicate data. So in this particular case, we're going to create an index buffer, and we're also going to have a position buffer, and then we're going to tell the GPU to render this in a different way. And we call, in the first part of this assignment, we call GL draw triangles, and you could draw it as an element, as a set of triangles, or a strip, or a fan, But here what we're saying, we're calling a different function, which is GLDrawElements. And GLDrawElements expects an index buffer to be defined. And so it will go and look at all of the index buffer. It will look at the first three indexes, go get the data from your position data and color data if it needs it, and then it will render that triangle, and it will do that all the way along. So we have we've looked at two ways of doing things. The one is GLDrawElements, and the other one is GLTriangle. Okay, I'm back. I needed to set up my Visual Studio. Here is part one. We just kind of walk through it and kind of see where we're going. We have our shaders at the top here. They're defined. You'll see that this part of what you're going to do in this assignment is you're going to change the shader based on the input. This component has a demo parameter here. If the demo is original or modified, you change that, see that. But the important part here is that here we have our source code for our shaders, and then here we create the shader, then we say we tell OpenGL, here's the shader source, then we compile it, and then we check to see if we have an error. We do the same thing for the fragment shader. We go there, we do the shader source and compile the shader. Again, check to see if there's an error, and then we create our program. We attach our shader and we link our program. And so now we create our buffers. I have two buffers here. One is this buffer. If it's modified, I change it to be that. And then now I go and I create a buffer for the array buffer. I add the vertices to it. And then I don't have an index array for this particular part of the assignment. And then I will do I clear the viewport, which you did last lecture. And then I basically down here, I say draw arrays, and I say it's of type GL triangles, so it knows to take three. So up here, so in this particular one, I have x, y, so I only have two values per vertex. When I tell OpenGL how to use this data, notice I'm using 2 here and not 3 of type float, and so that's fine. But again, the data, what the data represents, in this case we have 2 values per vertex, and we have down here, we're saying we use 2 vertices, 2 floating point values per vertex, and then here we say render the triangles. Now let's look at our shader up here. Our shader basically takes the position and we add 2 values to it. So remember, in our example we had z equals 0. Here we're just adding the 0. Just for this example, that's all we need. Okay, so let's run that and we can see what we expect here. Let's run this again here. And then let me pull this window into here. And so there's my original, and there's my modified. So I've just changed it, and that's kind of what we're going to do for the first part of the assignment. Okay, that's that. Now let's go and look at the second one. The second part of this assignment is down in this canvas.gl. In this particular one, we have the models. So basically, I'm creating these 2 models. As part of what we're going to be doing in this exercise is we're going to be generating these numbers. Notice I have vertices and colors. We'll talk about that in the lecture. But here's my indices. So this particular object here is defined by 1, 2, 3, 4, 5, 6 triangles, and they're defined by, so the first triangle is defined by this data, and then probably that one, number 5, like that. So let's run this one and see what this one does. Run part 2. Yes. And so my this is what your assignment will end up looking like. I can render a full array of triangles. So I have 6 triangles, and I've specifically arranged them so that they're in this order, so that when you're debugging it, you can actually see what's happening. And then there's also a hexagon, which is defined by 6 triangles again. And so all we're doing for this particular parameter here, when I look at my OpenGL or my GL canvas, you'll see that down here I'm changing this parameter here, which is the parameter that slider is setting. So that's what we'll be doing in class. That gives you kind of an idea of where we're going. Looking forward to spending the time with you this evening, getting this stuff done. It's pretty exciting. Pretty soon we'll be doing 3D graphics, and we will be seeing some pretty cool stuff on the screen. All right. I hope this was informative and prepares you for the lecture tonight. Come ready to do some coding. Thank you very much. I will see you later. Bye.